So I wanted to take a minute just to go through the conclusion that we talked about in class to the rubber stopper lab. So we plotted a data set with looking at the tangential speed of the rubber stopper versus its radius. And at first glance, that relationship between the two variables probably looked a little bit linear, but after maybe trying a few different linearization factors, hopefully you came up with better correlated data, even if it was just a little bit of improvement. As I mentioned, this lab has a lot of experimental error, looking at velocity squared versus the radius. So writing the equation of that line, we get that the velocity squared is equal to some number, meters over seconds squared over meters times the radius. Simplifying the units on that slope, we get that the velocity squared is equal to some number, meters per second squared, times the radius. So this slope, which when we're determining what the significance of the slope is, we kind of ask ourselves two questions. One, the slope on my graph is constant, so the significance of the slope is going to represent something that was constant in our lab and something that could be possibly expressed in units of meters per second squared. Well, the unit part is easy. It looks like acceleration, but we started the lab talking about how the rubber stopper would be moving with a constant speed. How can it be accelerating but still moving with a constant speed? So how can that happen? Well, if you remember, we defined acceleration as the change in velocity over time. These two quantities are vector quantities. So you can change your velocity by increasing your speed, you can decrease your speed, and because it's a vector, you can change direction. So in this context, when we are talking about uniform circular motion, it's certainly moving with a constant speed, but it's constantly changing direction. Therefore, it is accelerating. So we give this type of acceleration where it's still moving with a constant speed but changing direction, we call it the centripetal acceleration. Centripetal acceleration. And we write it a little bit differently, so instead of writing v squared is just equal to a times r, we get a little subscript c to stand for centripetal times r. Rearranging the equation, we get v squared over r, and that's our equation for centripetal acceleration. Okay. If we apply Newton's second law, which we remember was the sum of the forces is equal to the mass of our system times acceleration. Anytime you have acceleration, you will have a net force applied to it. So in this case, the net force for something that is moving in a circle is going to be the force or forces that are responsible for keeping it moving in a circle. And we give it a little bit different name, just like the acceleration. We call it the centripetal force is equal to the mass times the centripetal acceleration. This centripetal force is not a new force. It is just another way of writing the sum of the forces. And in this context, we're specifically just talking about the force or forces that keep it moving in a circle. So let's go back to the rubber stopper lab. All right, so if I look at a top-down view of the rubber stopper, it will move in a circle. Here's my rubber stopper, and here is the string. So in this case, it was the string that was keeping this moving in a circle. In fact, if I snap the string and cut it, well, if this thing was moving in a counterclockwise fashion, then this thing would take a straight line path. So if I cut that string, that rubber stopper is not going to spiral away. It's not going to go in towards the center because that's the direction of the tension force. It's going to just travel in this straight line path. And this is called the inertial path, and refers right back to Newton's first law that an object in motion stays in motion, object at rest stays at rest unless acted upon by an outside force. So this outside force was keeping it moving in a circle and accelerating. Once it was gone, it's just going to continue in a straight line path the entire time. Newton's first law. So let's just look at our lab a little bit more closely and talk about what kind of error analysis could we look at. So if we remember our free body diagram, we had the rubber stopper, and now that we're looking at a side view, this was our tension force, and then we had a tension force, and then we had the hanging mass right here, and that was equal to the weight of the hanging mass. So if this hanging mass wasn't moving, this weight was equal to this tension force, which was equal to this tension force, and in the context of this lab, the centripetal force is the tension force. So if we look at our centripetal force is equal to our mass times acceleration, this tension force is going to be equal to the weight of the hanger times should be equal to, this is our question of our error analysis, times our centripetal acceleration. This is going to be the slope of the graph. And this mass right here is the mass of whatever was moving in a circle. So this is going to be the rubber stopper only. Rubber stopper. Okay? It wouldn't apply to the mass of this weight because that's not what was moving in the circle. Only the rubber stopper was moving in the circle, so that's the m that goes in the equation. So you can go back and look at your data, and I know the data was a little bit flawed, but if you look at the weight of your rubber stopper, and most of you probably used 100 grams or maybe used 200 grams, so convert that into the weight in newtons. That should be 0.98 newtons or 1.96 newtons, depending what you used as your hanging mass. That would be the tension in your string. You should have the mass of your stopper somewhere written as one of your control variables, and compare it. Multiply that times the slope of your graph and see how close you got. So that's just looking at the rubber stopper lab.